problem you have during this, you can just approach me, or Manju is there always. Okay, with that, I guess I would like to welcome all of you, and I hope that you will have a very nice week of talks, and I'd like to ask Abhishek to share. Okay, we have also given a bottle in your bag. So basically, we have not given any bottle plastic water. So there are water, this RO waters there. So you can just basically fill up the bottles. Maybe just rinse it the first time, the bottle. But okay, after that, you can.
Okay. Yeah. Yeah. Okay. Thanks.
6 minutes.
Huh?
5 minutes.
Okay.
Okay, good morning, everyone. So my name is Abhishek Dhar, and I'm chairing the first session, which has two talks. First one is by Shotto Mojumdar, and second one was by Hugo Tusher. So I think if you want to ask questions, please use the microphone because this is being recorded and it will be on YouTube. So it's good if you use the microphone. So I think there are a couple of microphones available. Just raise your hand and then ask the question.
So David, careful of your jokes.
Yeah, everything is recorded. So we. But yeah. Okay, so I think we can start.
Okay, thank you, Abhishek. And so good morning, everybody. And let me start by first thanking Sanjeev for inviting me and also for organizing this conference. And it's really great to be back here after 4 years of pandemic. Thank you, Sanjeev. Okay. So I'm going to talk about correlated resetting gas and I'll explain to you what I mean by that. And this is some recent work which was done by my PhD student Marco Biroli and also in collaboration with Hernan Laralde and Gregory Scher, who is here. And this is published recently, and there's a longer version available in the archive. And more recently, I mean, there's a nice extension of this work, more related to more experimental systems. And this was done in collaboration with Manus Kulkarni, who is also present here. Okay. So this will soon appear, hopefully, in the archive. All right, so here is the outline of my talk. So I'll start by giving a sort of overview of a correlated gas in thermal equilibrium, okay? I'll talk about several examples and observables. So this will be the first part of the talk. And then I'll talk about the correlated gas, but in a situation which is out of equilibrium and in a stationary state. And this out of equilibrium stationary state is actually induced by stochastic resetting, and I'll explain to you what I mean by that. And then it turns out that even though this is a system of strongly correlated variables, you can actually calculate various observables exactly. For instance, average density of the gas, then extreme value statistics, order statistics, spacing between the particles, full counting statistics, etc. I'll define all of them as I go along. And then I'll conclude with a summary. All right, so let's start with the correlated gas in thermal equilibrium. This is a very old subject. So, and for simplicity, I'll just focus on one dimension now, but you can generalize it to higher dimension very easily. So the scenario is the following. So imagine that on a line, you have n particles with coordinates x1, x2, x3, xn. So the configuration of the gas is specified by these coordinates. And they are subject to an external confining potential, Vx, which can be harmonic or non-harmonic, whatever it is. And most generally, you can write down the energy of the gas as the sum over I V of xi. So this is the external potential term. And then there could be interaction. It could be two-body interaction, or it could be three-body interaction. It could be all types of possible interaction, all-to-all interactions, and so on. Okay? So in general, this is the energy function which is given to you. And we assume that the gas is in thermal equilibrium, which means that the joint distribution of the position of the particles or the probability of a configuration is just given by the Gibbs weight here, Gibbs-Boltzmann weight, where beta is the inverse temperature. And 1 over z is just a normalization constant which normalizes to 1, so it's a partition function of the gas. And now, the point is that, when you have interaction, okay, so this is this interacting term here, then the joint distribution does not factorize into individual distribution, which means that the gas is actually correlated. Okay, if you didn't have these red terms here, then of course it will factorize, and that will be the ideal gas. But otherwise, there's correlations, non-trivial correlations between the particles, and this fact of correlations between the particles makes this problem quite non-trivial to calculate any observable. And this problem has been around for more than 2 centuries, and a lot of people have worked on different models and so on. But of late, it has seen a resurgence of interest due to experiments in cold atom systems, where you can actually, with optical traps, you can generate all types of potentials, and you can even tune the interactions, and you can probe observables to very high precision, which were not possible before. So there is a kind of resurgence of interest in this correlated gas. And so let's just see what are the observables, natural observables that you would think of. So I have this, joint distribution, or probability of a configuration is given by this Boltzmann weight. So given this energy function, so you know this exactly. And now we want to calculate several observables. So what's the first observable? So this is the average density. That means just a fraction of particles on an average between x and x plus dx, and it's normalized to 1, because I'm dividing by 1 over n, you have n particles, okay? So this is just the average density of the gas. So, this is a non-translational invariant system because of the potential, external confining potential, so the density is not going to be uniform, flat density. In general, it will have some structure. So this is a macroscopic observable, if you like, average density. And then you can go into the microscopic observables, namely, you can, for example, just look at the positions of the particles and you can order them so that this is the rightmost particle, this is the second rightmost particle, third rightmost particle, etc. So M1, M2, M3. So M1 is the, if you like, the maximum of the X size, and M2 is the second maximum, and so on. So these are called order statistics. And then you can ask, the gap statistics. That means spacing between the particles. So for example, the spacing between first particle and second particle is D1, then D2, etc. So what are the statistics of this decay given this joint distribution? Okay? So this is called the spacing statistics. And then the last one is the full counting statistics. That means you take any interval minus L to plus L, and you just count the number of particles there, NL. And NL is going to be a random variable because the underlying probability distribution, there is a probability distribution, so this is a random variable which will fluctuate from one sample to another sample. And you can ask, what is the distribution of NL given the total number of particles? Okay, so this is called the full counting statistics. So there are all these observables, and in general, they are very hard to calculate for a correlated or interacting gas, in particular when there is a long-range interaction between the particles. So the easiest example is when there is no correlation, which is just the ideal gas. Okay, so just to tell you that in the case of ideal gas, when there is no interaction between these particles, a non-interacting gas, so the total energy is just the sum of the external potential, V of xi. So in that case, you see immediately that when you write e to the power minus beta exi, it factorizes into individual probability distribution of the particle. So each particle is drawn from this P of x, which is just e to the power minus beta Vx normalized to 1. And in that case, you can actually calculate all the observables very easily in terms of this P of x. So for instance, average density, you can just put this P of xi and just compute this. So you see that this just becomes P of x. It's very easy to see this. And distribution of the maximum M1, so the rightmost particle. So that's also easy. To calculate this, you just ask for what's the probability that the maximum is less than equal to some number W. This is the cumulative distribution. If you know the cumulative distribution, you can calculate the PDF by taking derivative with respect to W. Now, this event that the maximum is less than equal to W is exactly the same as the event that all the particles are less than W, their positions. So which is, and since the particles are independent, so this is just Px prime dx prime minus infinity W to the power n, because there are no correlations between the particles. And then, for large n and large W, this approach is a scaling form depending on the tail of P of x, and one recovers the, well-known extreme value statistics laws like Gumbel distribution, Frechet distribution, and Weibull distribution, etc. I'll not go into the details of those. And similarly, you can calculate the distribution of the kth maximum or the kth gap decay, okay, between these gap statistics. So essentially, for ideal gas, you can calculate all these observables. And last one is the full counting statistics, and this is also easy to calculate because, for a particular particle, what's the probability that it falls between minus L to plus L? So this is just this integral here. Okay? So this is the QL. This is the probability with which a single particle will fall in this interval, and you have n particles. So therefore, this distribution is just a binomial distribution with QL as the probability of success and 1 minus QL as the probability of failure. Okay? So essentially, all these observables you can calculate very easily for ideal gas. But of course, the moment you have interactions between them, it becomes a very hard problem. Okay? So I'll now first talk about the example 1, which is the very famous example. It's called the Dyson's log gas. So here, the energy function, again, you have a harmonic potential. So this is n by 2, and I rescale the xi by square root of n such that both the first and second terms, they are both of the same order. So this is the external harmonic potential term. And then each pair of particles, okay, not necessarily nearest neighbor, I mean, they repel each other by the log interaction, logarithm of xi minus xj. Okay? So this is the famous Dyson log gas. Dyson studied in 1962, and he studied in the context of random matrix theory. So let me just very briefly tell you how this model appears. So I mean, Wigner-Dyson, they were looking at the, describing disordered, system or nuclear physics, etc., by a random matrix. And so you take an n by n random matrix Hij, whose entries are Gaussian, and this is a Hermitian random matrix, okay? And so what you do is you assume that this represents a sort of Hamiltonian of a disordered system, and the entries, they are just Gaussian variables, independent Gaussian variables. So therefore, the joint distribution of the matrix entries, this is just the product of the Gaussians, which you can write down as trace of H dagger H. And the point about this is that this particular form is that if you now make any rotation, so you are looking at a Hamiltonian, so the physical property should be invariant under a change of basis. So if you make a rotation of the basis, that means you make a unitary transformation of this H, then this trace of H dagger H is invariant under this unitary transformation, and that's why it's famously called Gaussian unitary ensemble. So given this entries distribution, you can ask what is the distribution of the eigenvalues. There will be n eigenvalues. And it turns out that these eigenvalues are very strongly correlated, even though the matrix entries are uncorrelated Gaussian. And we cannot actually computed the joint distribution. And this is given by, there's a Gaussian factor here, but there's an additional factor, which is called the van der Monde term, okay, which makes these guys correlated. If you didn't have this term here, they would be uncorrelated, it will be product. But because of this term, it makes them strongly correlated. And this is the famous eigenvalue repulsion, because you see that the probability that two eigenvalues are very close to each other vanishes as the power of the distance between them. And this is the eigenvalue repulsion that is well known in quantum chaos and nuclear physics and other systems as well. And in fact, you see that this van der Monde term, x squared, you can always write as e to the power 2 log x, and therefore you can write it in the Boltzmann form. And this is the confining potential, harmonic potential, and this is the logarithmic repulsion between any two eigenvalues, basically. Okay? So you can interpret these eigenvalues as the positions of charged particles, n particles, on a line, which are subject to external harmonic potential and repelling each other by the pairwise log repulsion. Okay? So this is beta equal to 2 because I'm talking about the Gaussian Hermitian random matrix. And now most of the observables that I've defined, they can be computed exactly for this, GUE ensemble, but they're not that easy because you have to use some thing called determinantal structure and so on. And, whole name of the game of random matrix theory is to actually study these observables for Gaussian ensemble. And so, for example, if you look at the macroscopic density of the gas, so this is the average density normalized to 1. So in the large n limit, this converges into what is called the Wigner's semicircular form. So that means all the eigenvalues are concentrated over a finite support from -√2 to +√2. So there are more eigenvalues near the center of the trap, and they go to 0 as you go away from the center of the trap. So this is the macroscopic density, and then all the microscopic observables you can also calculate. For instance, if you look at the largest eigenvalue, which is the, in my notation M1, that is the rightmost particle in charges in this system, one-dimensional system. So it has its mean value √2 because that's the age of your density, and it fluctuates around this mean value on a scale whose typical fluctuation scale is n to the power -2/3. And if you look at this scaling function on this scale, it is what is called famously the Tracy-Widom distribution, which has now been measured in many experiments, and there's a huge literature on that. I'll not go into the details, but with Arnaud, Paul, and Gregory, both of us here in the audience, we wrote some recent review on this extreme value statistics of correlated random variables. So if you are interested, you can have a look at that. Okay, so this is number one example. So you see there's a lot of activity just for, just one pair, two-body interaction. It makes the problem extremely hard. The second solvable example is what is called the Jellium model in one dimension. So this is now again a harmonic potential, and now you have a linear repulsion, not log repulsion. So this is like a real Coulomb gas in one dimension, because Coulomb gas in one dimension have repulsion which is linear. And this has been again studied by various people in the 60s and so on. And what is known is, for example, so alpha is the interaction here. What is known is that in this case, the density again is supported over a finite interval, but the density is completely flat here. Okay? So it's a constant in the large n limit here. And more recently, the other observables like extreme order, gap, full counting statistics, so they were actually, we computed them mostly in collaboration with the ICTS team, Abhishek, Anupam, and Sanjeev, and also with Anna Flack, who was a graduate student working with me, and Gregory. So again, many things you can compute here, and also I forgot to mention Manos also. And so this is the, another example of correlated system where you can make, some nice solutions, exact solutions. And then you can generalize this to what is called the rise gas. So again, you have a harmonic potential, but the interaction now is in general xi minus xj mod to the power k, again pairwise interaction. And the sign of k is such that it's always a repulsion. And the k has to be bigger than -2, because if k is less than -2, then what happens is the repulsion is so strong that harmonic potential is not able to confine this gas. Okay? So we'll assume that k is bigger than -2. So this is called Rees gas, which is which was studied, introduced by Rees in 1938. And the special cases of this Rees gas, when k, this index k, is -1, this is the Jellium model, linear interaction, linear repulsion. K goes to 0 limit, this is just becomes the log gas, because k goes to 0 limit, you can express this as a log. And k equal to 2 is what is called the Calogero model, which is inverse square repulsion between the particles. Okay? So in general, I mean, essentially this problem is very hard to do for arbitrary k, but recently we made progress in calculating the average density, that is the macroscopic density. You can calculate it for all k bigger than -2, and this is a work done with again the ICTS team, and also in collaboration with David Mukamel, who unfortunately could not come. And then also there have been recent progresses on the gap statistics and so on. So Abhishek and Manoj and other people from ICTS, they have worked also on these problems. Okay, so to summarize this part, essentially, so I'm saying that sort of gas, correlated gas in thermal equilibrium, even though the stationary measure exactly, which is just a Gibbs measure, because of the correlation, any observable that you can measure experimentally is very hard to calculate analytically. Okay, so only for a few examples exist, and each of them is a sort of model with its own lifetime, and people have spent enormous amount of time, and so people are still searching for more solvable models, integrable models, if you like, and integrable in the sense solvable models, and also these the cold atom experiments. These models are playing more and increasingly important roles. Okay. Yes. Sorry? Sign of k. Yeah.
Can you motivate why?
I said it, you didn't listen. So this is because I said that in order to make the repulsion, okay. So if k is positive, then of course this is 1, and then it's a repulsion term. If k is negative, okay, so you have to make it this sign as negative, okay, in order that it's a repulsive interaction. Okay. All right. So now what I'll do is that I want to talk about, so far I was talking about thermal equilibrium, and now I want to talk about the non-equilibrium stationary state, again a sort of correlated gas, and this correlation actually is induced by stochastic resetting, and I know there will be many talks on stochastic resetting in this conference, so I just wanted to just tell you a little bit overview, not all aspects of it, just to motivate this problem here. So stochastic resetting is sort of, this was essentially the motivation for studying stochastic resetting. It came from search problems. So as you know, search problems are ubiquitous in nature. So for example, animals searching for food, then helicopters searching for survivors after a shipwreck, or even a protein searching for a site to bind on a DNA, or even more mundane example of, when you are writing a computer program and you are debugging and you want to find the bug, basically. Okay? So now in all these examples, it's quite natural that if you search for a while in vain and don't find the target, you might probably, a natural intuition tells us that you might stop and restart the search process, either from the same initial configuration or from any predetermined fixed configuration or any random configuration, if you like. And maybe that, the rationale is that, when you restart from another point, then maybe you will find a different pathway to explore, and you might find your target more easily, okay? I mean, for example, if you are doing computer program, then, you don't find your bug, you're getting tired and all this, so you just take a coffee break, come back and restart, and then you might find the bug more easily. Okay. So another example is that, if you take any complex system like spin glass, for instance, this is a sort of, if you plot the energy of the configuration, different configuration, and this is the energy landscape, and so each point on this, things represents the energy of a particular configuration. So this is like configuration axis, if you like. And so you can start from any configuration, and you can do a local dynamics like simulated annealing, where you just flip a spin, for example, and you move from one configuration to another configuration. And so what happens if your temperature is low enough, then your goal is to find the global minimum, the ground state of your system, and you might actually get stuck in a local configuration for a very long time. And so again, people have observed empirically that it's a good idea to actually, when you are stuck for a while, I mean, just go back to either through starting configuration or any other fixed configuration or random configuration, and you restart the search. And again, the rationale is that you might this time find a different pathway, and you might find the global minimum more easily. Okay. Now, these ideas have been around for a while, and that somehow the resetting is helpful, but empirically, but there was no quantitative estimate for it. So about 12 years back, with Martin Evans, who is present here in the audience, so we decided to to address this question within a very simple toy model and ask sort of does resetting really help finding the target, for example, okay, to minimize the search time and so on. And since then, in the last 10 years, there have been enormous number of studies on this stochastic resetting problem, addressing different aspects, and many different models. And basically, the conclusion is that indeed, generically, this actually helps. Of course, not always, but generically, the resetting helps to improve the search time of a target. So that is one aspect of the problem. And the second aspect of the problem is that the stochastic resetting actually induces a non-equilibrium stationary state. And so today's talk, I'm not going to talk about the target search problem at all. I'm just focusing on the non-equilibrium stationary state aspect of this problem. Okay? So let me just, just to set the stage, I mean, I just remind you just this basic simple model so that we get the ideas clearly. So the basic model is just a one-dimensional diffusion. You can define it at higher dimensions also, but let's just look at the one dimension. Okay? So you have just a single diffusing particle, let's say starts at the origin. It undergoes free diffusion, and after some random time, drawn typically from the exponential distribution, you just reset. And here I'll just consider the simplest version where you reset to the starting position, that is the origin. You reset instantaneously, and then immediately after that it starts diffusing again, and then you reset again after random time. So these intervals between successive resettings, they are independent and each drawn from this exponential distribution, where this R is like the resetting rate here. Okay? So that's the model, very simple model. So if you're doing simulations, so you are doing dynamics in continuous time t, so in a small interval delta t, you update the position of the particle by saying that the position x at time t plus delta t is either 0 with probability r delta t. So this is the probability and r is the rate. This is the resetting rate. And with the complementary probability 1 minus r delta t, you just do diffusion. That means you just add a sort of noise to it, to the current position, and this noise is delta correlated, and d is the diffusion constant. So r is the only new parameter here. This is the resetting rate. And so you want to ask, what happens when you switch on this resetting rate. Okay? So what I want to calculate is first the basic object, which is what is the probability density of the particle to be at x at time t in the presence of the resetting with rate r, starting from the initial position at delta x, basically. So we all know when there is no resetting, when r is 0, it's just a plain simple diffusion. So therefore, P0 of xt is just a Gaussian, and this is 0 mean Gaussian with the diffusion constant d. So now the question is that if I switch on this resetting rate r, what is the stationary state what is the state that happens? Okay. So notice that when r equal to 0, there is no stationary state. You have a Gaussian whose width increases like square root of t, and there is no long-term stationary state here. So to solve this problem, so it's very easy actually. So I just this is the only little math here. So essentially, you write down the Fokker-Planck equation. So PR of xt. So there will be a diffusion term, of course, and then there's a resetting induced term. So what are these terms? So there's a loss term. This is master equation. So there will be a loss term from x with rate r to the origin. So this is a loss term, and there will be a gain term. If you happen to be exactly at the origin, you might come from some other point x prime by resetting with rate r to the point at the origin, and then you have to integrate over all possible final positions from which you can reset to the origin. Okay? So, and because this probability is conserved, so this object is exactly equal to 1, and therefore you have a very, very simple equation, which is diffusion equation with a with a loss term, constant term here, and with a sink term, a sink and a source term, which is localized at the delta function. So this is a linear equation. You can trivially solve it just by taking Fourier transform, and I'll not go into the details, but the solution of the Fourier transform you can write in a very suggestive form, and this is the exact solution of the problem. You can check by substituting in this Fokker-Planck equation. It satisfies the initial and boundary conditions. But there's a nice physical interpretation of this term in terms of the renewal equation. So what it means is there are two terms in it. So let's look at the first term. So first term is e to the power minus RT P0 of xt. P0 of xt is just the guide, basic bare diffusion basically, propagator. So this means that there is a possibility that when you go from here, there is a possibility that there is no resetting at all between 0 to t, which happens with probability e to the power minus RT. And in that case, it's just a free propagation. So you have, so this term here corresponds to when there is no resetting at all. But then you might have one or more resettings. So in that case, what you do is, what is enough is to track the time at which the last resetting happened. So suppose that this is the tau behind the observation time t. Because, you don't care what happened before that, because you have reset at the last here. So after that, it's a free propagation, okay? So what is the probability that there is no resetting event in this tau? So that's e to the power minus r tau, followed by a resetting event, which is r d tau. You don't care after that what happens. And in this time interval, you have a free propagation. So this is just a P0 of x tau. Okay? So this is very general, actually. I mean, it doesn't have to be diffusion. It can be any other stochastic process, if you like. Okay, so this is just a renewal approach. So all you need to care is just this tau, time since the last resetting. Okay? And once you have that, then you see that, immediately if you take the t going to infinity limit, the first term drops out, and you have an integral 0 to infinity of this object here, and this is diffusion. If you just substitute this, you find a non-trivial non-Gaussian distribution. It's a double exponential distribution. Okay? So the first point is that there is indeed a stationary state. Okay? So when r equal to 0, there is no stationary state. Okay? As you see from here, this term is not there, and P0 of x tau is always time dependent. But now when you introduce the resetting, it induces a stationary state, and physically this is easy to understand because diffusion is trying to spread the particle away from the origin, whereas resetting is trying to push them back towards the origin. So there's a competition between the two, which leads to a stationary state. Okay? So this is the exact solution, and but the main point is that this is actually, even though this looks like a Gibbs state with an effective potential alpha naught mod x, alpha naught is square root of r over d, but this is actually not a Gibbs state because this is a non-equilibrium stationary state. And the reason is because there is a non-zero current in the probability space, if you like, because by resetting, you are always going back to the origin, but there is no reverse move. So the detail balance is manifestly violated. And so it's a very simple example of a stationary, non-equilibrium stationary state, if you like. And this prediction was recently verified in the optical trap experiments using holographic tweezers from the group of E.L. Wickman, and Ornobo here was also involved in this work. And so this was basically 12 years back when we predicted this, okay, this stationary state. All right. So now, I mean, immediately you see that with this toy example, that once you have this renewal idea, you can actually generalize to any system, actually, classical, quantum, many-body system, anything. So the main idea is that you have any system, x of t just represents the configuration essentially at time t. It has its own natural dynamics. For example, it could be just the coordinates of many particles, a single particle, or it can be spins in an Ising model, whatever. It has its own natural dynamics, or it could be just a state of a system in the quantum setting. There's just a state which is evolving by unitary evolution. So it has its own natural dynamics, and you interrupt this natural dynamics at random times and send it back to either the initial configuration or some other configuration you like. And then you let the dynamics take over again, free evolution, natural evolution, and then again at random time you reset, and so on and so forth. Okay. So and the main point is that these intervals between two successive resettings, these are independent and drawn from some arbitrary distribution p of tau. And Poissonian resetting that I discussed about before, this corresponds to just choosing exponential distribution, where r is just the rate at which this resetting happens. So as I said, this is very general. You can do it for classical, quantum, anything you like, okay, and easily generalized to sort of many body systems and so on. Okay, so for instance, I mean, two simple examples are just if you take fluctuating interfaces, for example, KPZ or Edwards-Wilkinson's interface in 1+1 dimension. Here, the basic degrees of freedom are the heights of the interface at different points in space. Or in the Ising model, these are the spins at different points in space. So it has its own dynamics. So for example, for spins in Ising model, you can think of it evolving by the Glauber dynamics. So what we want to calculate, what is the probability that the system is in configuration C at time t, in the presence of this resetting R. And when you reset here, you reset the whole configuration to its, let's say, initial position. And again, you can write most generally this kind of renewal equation that the probability distribution of the configuration as C at time t in the presence of resetting. There are two terms, one when there is no resetting at all, and then when there are one or more resettings. And again, this tau here is interpreted as the time since the last resetting. So this is a very general equation. So all you need to know is the probability distribution of the configuration in the absence of resetting at all time tau. And then you can actually calculate this object in the presence of resetting. And in particular, a long time limit, if this integral exists, then you reach a non-equilibrium stationary state. And to characterize this non-equilibrium stationary state, but notice that you need to know the full dynamics at all time tau, not just at late times, okay? And in the absence of resetting, because this is just a Laplace transform of that object. Okay? So again, this is a very general thing. And so now what I want to do, so this has been studied for fluctuating interfaces and Ising model and so on. But now in the rest of the talk, I'll just focus on a particular simple example, which is motivated by the recent experiments. So this is what I call correlated resetting gas. So let me just explain to you. Yeah, sure.
Is that mic? Yeah, I just missed one thing, I think. When you reset, in the more general example, in these last examples, you reset to what configuration?
You start from, let's say, Ising model, you start from some arbitrary random configuration, okay? Let's say all spins are random high temperature configuration, okay? Whatever configuration you start with, you reset to the, let's say, same initial configuration.
Right. No, I'm saying where is that? Okay, I'm just missing something. The PRSCT is the distribution in configuration space at time t.
Right.
Where is the? I'm just obviously missing some point.
Yeah.
Where is the configuration to which you reset?
Yeah. So here I'm saying that to the initial configuration, subjected to resetting to the initial configuration.
Oh, I see.
So simply, okay. So I mean, if you take Edwards-Wilkinson, you start from a flat initial configuration.
Okay.
Evolve it up to a random time, and just reset. That means you restart again from flat initial configuration.
I see.
Okay. All right. So this is motivated by the recent experiments. So there's this. I mean, these are optical trap experiments, and so the first one I mentioned already from the Yael Roykman's group from Tel Aviv, and the second one is from Sergio Siliberto's group in École Normale at Lyon. And I was involved with their experiments, so I'll talk about more or less this system here. So here, they wanted to first figure out, I mean, just compute the single particle case. Okay. Now, how do you actually, reset in real experimental labs, right? I mean, in computer simulation or theoretical calculation is very easy. You just, instantaneously reset the particle. But how do you do it in real experiments? So the way it's done is the following. So what you do is, you take an optical trap and you take let's say, single particle diffusing in this optical trap. So initially, you let the particle undergo free diffusion for a while, and then you switch on the trap, the harmonic trap typically. When you switch on, so that's like mimicking the resetting basically, and you take a very steep trap to reset to the origin, and you let the particle thermally equilibrate inside the trap, and during that time, you don't take any measurement, and then again, you switch off the trap and let the particle diffuse. So there are these two alternate states, so more precisely here. So free diffusion for a certain period, which is typically random, let's say, and then you switch on the trap, and during this, when the trap is switched on, of course here, I mean, you don't reset to a particular position, you reset to a thermal distribution of the particles inside the trap, which is a Gaussian distribution. And then you switch off the trap again, and then again let the particle diffuse freely, and then switch on, and it just goes on like that. Okay? Steps 1 and 2 alternate. So, and then they measured, various objects, I mean, like, mean first passage time, and, it sort of matched pretty well for single particle systems with our predictions. But in the real experiments, what happens is that you never have one single particle, right? You have a dilute system, you have few particles, okay? And they are usually interacting by a hydrodynamic interaction or whatever long-range interaction. But, often you can actually tune these interactions. So the simplest model that we thought of is to just take n non-interacting particles, okay, inside this trap, and you do this protocol here, okay? That means you let them freely diffuse, and then you switch on the trap, let them freely diffuse, switch on the trap, and so on, alternate, okay? So that's the model. So what happens here, the interesting thing is that even though the interaction is not there directly between the particles, because they are all in the same trap, when you switch on the trap, they all fill simultaneously this resetting, and that actually generates a dynamical correlation between the particles. Okay? So that's why it's sort of interesting, and so let me just define precisely the model. So we have this, so let's say we have n particles which are totally non-interacting, independent particles. So you let them evolve up to a random time, and you simultaneously reset them. So that's like switching on your optical trap to the origin, let's say. And then again, this is instantaneous case, and then you let them evolve again randomly, and again you switch on at random times the optical trap, and so on and so forth. Okay. So then the question you ask that, what is the joint distribution of the n particles positions after a long time t? And again, from the general thing that I discussed about, you see that this, there will be a stationary state in the long time limit, and so there is the first term which has gone to 0 when t goes to infinity, and you have this r 0 to infinity d tau e to the power minus r tau. Again, tau here is the interpretation as the time since the last resetting, okay? Times the, without resetting, and without resetting they are totally non-interacting, so it's just a product of the Gaussians, basically free diffusion, okay? So it's actually very, very simple. So essentially, you have independent gas, ideal gas if you like, with a parameter tau, which itself is drawn from an exponential distribution if you like, okay? So that's a very, very nice structure. But the point is that this is a correlated gas because, the joint distribution does not factorize. It factorizes inside the integral, but not when you do the integral over tau, okay? So therefore, it creates these correlations, which is dynamically created, not built in, okay? So, so the interactions between the particles are not built in, but the correlations are generated by, it's emergent correlations from the dynamics itself due to the simultaneous resetting. When they're all the time, you are pushing them all together. So somehow that creates an effective attraction between the particles dynamically, and this leads to a stationary state with a non-trivial correlations. In fact, you can calculate the correlation function very easily. Of course, if you calculate the standard correlation xi xj minus average xa, that will be 0 because this is Gaussian, so xi xj when I not equal to j, this will be 0. But so the first non-trivial correlator is xi square xj square minus average x connected part basically. And you can show that this is very simply, this is just 4d square over r square. So this is positive, which means there is an attractive all-to-all interaction between the particles in this gas, okay, in the stationary state. And the nice thing is that, the point is that even though this is a strongly correlated gas, everybody is, connected to everybody basically, but you can still calculate all the observables very simply because of the structure, the solvable structure of this joint distribution. Because, this guy here inside the integral is like an ideal gas, right, with tau as a parameter. So you can actually compute all the observables that I showed you in the first problem. This is like an equilibrium problem, if you like. If you think of this tau, this is just independent Gaussian distributions. So you calculate all the observables for this ideal gas, and then you just have to, integrate over this tau variable, thinking of this tau as a random observable, basically. So this is the nice thing about this model that, even though it's a strongly correlated system, it sort of gives you a very nice mechanism to generate a solvable many-body system. And we can actually calculate all the observables that I mentioned in the beginning, namely the macroscopic observable like average density, the distribution of the kth maximum, which is the order statistics, then spacing distribution, full counting statistics, etc., etc. Okay? So let me just flash through the results now, because you know roughly, basically I want to calculate all the observables for the ideal gas, and then I just have to integrate over this. Okay? So I'll just tell you the results. So average density is very simple. So average density, because this is just the expectation value of delta of xi minus x. So when you take this joint distribution and you do this, so it just becomes 1 point marginal. Okay? So this you just keep x1 equal to x and integrate over all the other guys. And when you integrate, inside the integral, they all factorize, so it goes out. So what you have is exactly as the single particle density that Martin and I had looked at a long time back. So it's just double exponential distribution. So that's the gas. Here it's not a finite support. It's supported over the full interval, okay? And it's maximum. There are more particles at the trap center, and then it sort of goes down exponentially on either side, okay? So same as this. So this is the average density, and with the width, which is square root of d over r. And then you can actually ask for example, for the order statistics, that is, for example, m1 is the position of the rightmost particle in the gas. So it turns out that this is the scale is typically square root of log n. And to compute this, what you do is you set k is the order basically. So k you set alpha times n. So if alpha is the order 1, you are probing in the bulk of the gas. And if alpha is order 1 over n, for example, k equal to 1, k equal to 2, you are probing at the edges basically. Okay? So it turns out when you do this computation that if you work in the bulk, you find that the probability distribution of the kth maximum counted from the right is actually given by a scaling function here with a scale which is some number which is order 1, and there's a non-trivial scaling function here. And similarly at the edge, when k is of order 1, it's exactly the same scaling function, because this is very different from random matrix theory. In random matrix, the bulk and the edge have very different properties, but here it turns out that this function, and the scaling function f is just very simple, is 2z e to the power minus z squared. So the point is that all the positions of the particles, the ordered positions of the particles, they all have the same scaling function. The scaling function is independent of k. So no matter whether you probe in the bulk first one or the 25th one or I don't know 56th one, they all have this exactly same scaling function. So in that sense, this is universal. And if you plot this scaling function and you can do numerical simulation, you can collapse them and it works perfectly well. So this is this universal scaling function here, which looks simple, but it's quite non-trivial. So it means that this sort of shows that basically all of them have the same scaling function. That means they are very, very strongly correlated in the stationary state. And then you can probe the gap statistics. So the gap is just dk, which is mk minus mk plus 1. And again, you can compute this scaling function. And again, corresponding scaling function h of z, which is now given by this function here. Details are not that important, but the main point is that this is again, no matter whether you probe at the edge or inside the bulk. So inside the bulk, the typical spacing between the particles is order 1 over n, whereas near the edge, it's actually 1 over square root of log n. But the scaling function h happens to be exactly the same, whether irrespective of whether you are in the bulk or at the edge. And only the scale factors are different depending on whether you are bulk at the edge. Okay? And once again, you can actually do your simulations and you can check that it matches perfectly well. And the scaling function is highly, non-trivial tail. So it goes to a constant, which actually shows, for example, in the random matrix theory, this is Wigner-Dyson distribution, so it goes to 0 because of eigenvalue repulsion. But here, the eigenvalues don't repel them, and they attract each other in some sense. So it goes to a non-zero constant when the gap goes to 0. So they can be next to each other, if you like, with high probability. But for large z, it has a non-trivial stretched exponential tail, which goes like e to the power minus z to the power 2/3, okay? Which is, again, sort of universal in this sense that no matter what it is. Okay, I'm done. And then you can calculate the full counting statistics as well. So these are just results I'm just flashing you, but it's very easy. Again, you work it out for the ideal gas, and then you just have to do the Laplace transform of that. So here, the full counting statistics, again, is a scaling function, probability distribution NL over N. So this is has a scaling form like that. And but the scaling function itself is quite non-trivial. So it is a very weird shape. So it has a peak here. And this is kappa. Kappa is just a fraction of particles inside your interval minus L to plus L around the trap. So it goes up, has a peak, and then it again diverges as kappa goes to 1. Okay. So, and it diverges in a sort of integrable way, 1 minus kappa times log 1 minus kappa to the power 3/2. And again, simulation matches perfectly well. So let me just say that, okay, you can now easily generalize it. I mean, here I talked about just diffusing particles, but, you can, as this thing, you can create a correlated gas by considering, for example, ballistic motion of the particles or Levy flights, whatever you want. And, but this provides a very, very simple mechanism to generate a strongly correlated gas, okay, which is strongly correlated and yet solvable. There are not many examples of that. And so in some sense, this is a sort of new application of stochastic resetting. And so let me just summarize then. So basically, I talked about a sort of very, roughly speaking, very, simple mechanism via stochastic resetting to generate a strongly correlated, non-trivial, non-equilibrium stationary state. But yet it is solvable for all the observables, which are not always easy to compute with strong correlations. And more recently, with Manos here and with Marco and Gregory, we looked at a generalization of this problem, which is more realistic experimentally, Namely, you have still independent particles, but your trap is going from mu1 to mu2, with rate R1 and R2. And this again creates very strong correlations, and we can actually characterize this stationary state completely. So I talked about this new application of stochastic resetting, but of course there are other applications of stochastic resetting that you will hear from many talks in this conference, and it's a very long list. And there are some recent review articles, one with Martin and Gregory, and one by Arnab and Shlomi Ruveni, and also Shamik Gupta, and so on. And there was a sort of nice JFISE article recently, special issue, which was edited by Anupam Kundu and Shlomi Ruveni, which talked about different applications of stochastic resetting. So it's a very nice special issue. Many things are there. So in a nutshell, stochastic resetting still happens to be a very rich and interesting, subject with many interesting static and dynamical phenomena. And let me acknowledge my collaborators. I had the good fortune of collaborating with many people on stochastic resetting. Many of them are in this room, and all these graduate students here, and also with Martin, with Fugo, with Manas, Kulkarni, with Gregory, everything. You can read your names, Sanjeev, of course. So thank you very much for your attention.
Questions?
Hi, Shotuda.
Sorry.
Yes, it was very nice and pedagogical lecture as well. So my question is related to what you talked about, the Coulomb gas problem.
Yes.
So your calculation was for beta equal to 2 case, right?
Yeah. No, but you can, beta equal to 2 is particularly simple.
Right.
Because you have the determinantal structure there.
Right. So there, my question was that for the Dyson log gas, if I correct that, there was a transition that happens at t equal to half. That's the work of Eisenman and others. So
T equal to, what do you mean T?
So beta equal to 2, sir.
Yeah.
Right. So
Beta equal to 2, what transition? No,
So there's a
generally,
there's
if you look at the Wigner's semicircular law, this is true for all beta. Okay. Beta equal to 2 has an integrable structure, but you can actually do the computation for any arbitrary beta now. Okay.
Okay.
So, for example, Tracy-Widom distribution depends on the beta, okay, which beta you take. But not Wigner's semicircle. Macroscopic profile, doesn't depend on
in the
beta.
transition, if you take in 1D, there is a transition from the fluid.
There is no,
to
I don't know what
solid.
transition you are talking about at beta equal to 2. There is a transition when beta is of order C over N, okay? Because, if beta is beta is like a inverse temperature, okay? So if temperature is very high, that means when beta is very small, then you can actually, have a spread from Wigner's semicircle, you can actually go into a infinite support, okay? And there the density depends continuously on this parameter C, when you said beta equal to C over N. But beta equal to 2, I don't know what transition you are talking about. At least I'm not aware of that.
Okay, so you can calculate now for any.
Yeah. In general, for any beta, but it's much harder. For example, if you take beta equal to 1, which is the GOE ensemble, the calculations are much harder. And similarly, beta equal to 4, these are the 3 classical beta ensembles. But now you have all beta ensembles. Beta equal to 4, you have a Puffian structure, which is much more harder to analyze. But what is nice about beta equal to 2 is that it has a determinantal structure. So it's like a free fermion, basically. Okay. So therefore, it's much easier to calculate various observables.
Okay, thanks.
So, quick question.
Yeah.
You mentioned some cold atom experiments.
Yes.
Could you tell us a little bit about them?
Well, cold atom experiments, for example, we have been talking to Saptarshi and, what's his name, Sangrita, who are here. And, this is the thing that we are working with Manus now. So essentially what you do is you can generate an optical trap, okay? And you have this, the atoms inside it. And you can actually change the frequency of the stiffness of the trap from mu1 to mu2, okay? And you can actually, they can even tune the interaction between these atoms with a phase back resonance or something. And then you can ask, for example, first thing to compute is the average density, or even okay. I think these edge fluctuations for the maximum and things like that, or gap statistics, they might be much more harder to compute. But the first thing we want to know is what happens to the average density, okay? So which you can calculate and to see if they can measure it. So we hope they will be able to measure it. So.
So slightly general question. So if the stochastic resetting you have is not dependent on a randomly generated time, but reaching some particular value of the variable that you're looking at the dynamics of, how much of this will it
So
carry
it
over?
depends on the precise definition of this, but I mean here I was just talking about resetting to the origin. I mean, but you don't have to always reset to the origin. Resetting position you can choose from a distribution.
Yeah, not the resetting position, not the resetting position, but supposing I reset when I reach a certain value of X.
Oh, I see, threshold, I see. Yeah, so this has been also studied. So for example, Sid Redner and Julian Ranjan Farling, so they have studied the case that, this happens typically in a electrical grid, like they studied the case of Canada where, when the voltage exceeds, certain value, then there's a failure basically, certainly, where demand is too much, then there's a failure of the network. So that means it's reset, the voltage when it exceeds some threshold value. And so this, of course, changes the details of the things, and but people have studied this basically. So the effect that this is called first passage resetting. That means when it reaches a level for the first time and then you reset. But you don't reset all the time basically. So yeah, so this has been studied also.
Yeah, I have a question that's related to Sriram's question. So if you have a system with many degrees of freedom, in principle, you could reset either to the initial microstate or to the initial macrostate, right?
Yes.
So like in simulated annealing,
Absolutely.
you would say you go to infinite temperature,
Sure.
so does that make a difference? Is it sort of an
Well,
interesting distinction?
the many body system with, this is absolutely a good question, and I think it does. I mean, this has not been studied systematically, okay? Because even for Ising model, I mean, I know only of 1 or 2 papers which have studied, just a global dynamics and you just reset to the initial configuration. It actually has a non-trivial phase diagram. I didn't have time to talk about that. And so if you now, choose your, configuration from a macro state, as you said, instead of a microscopic configuration, I think, it will have different behaviors. Like we know, I mean, for example, even in the single particle diffusion thing, in the Siliberto's experiment, the actual experiment, the distribution has a finite width. And there we found that, this sigma, finite sigma, because in the theory, we're just doing a delta function resetting. But when you have finite sigma, it has actually a non-trivial effect on the mean first passage time and so on. So that in the many-body context, unfortunately, has not been studied yet. So that's a wide open problem, basically.
Possibly related. When you do a reset in the experiment, I noticed the experiment seems to use a protocol called engineered Swift equilibration.
Yes.
But in practice, when you have n colloidal particles and you create a trap, you catch all of them, their movement affects each other through the ambient fluid.
Yes, absolutely.
Right.
So I said, I mentioned that there's a hydrodynamic interaction between these
And
particles.
that the ESE is a way of somehow suppressing that as to the extent possible.
Yeah, I mean, in
or
some
what?
sense, I mean, ESE is essentially, if you know the final state, I mean, you can somehow go there much faster than the usual dynamics, basically. So,
Right.
But, it doesn't always work. In this case, it seems to work. That's what he tells me. I don't know exactly how it works, but, I mean, it seems to work. And they can, so, during the, basically, so they let the particle relax into thermal equilibrium. Normally, it should take a long time.
Right.
But with this ESE technique, they just make it relax very fast, basically. So, this adiabatic shortcut to relaxation, basically.
I
so,
see. But otherwise, in general, the kinetics of the reset, the internal makes a difference.
Absolutely,
And that's somehow an impossible calculation.
No, that will be very hard. But even I would be very interested to do this computation, like when these particles N are not independent, but there is already some kind of hydrodynamic long-range interaction between them, and then you switch on the trap, do resetting. What happens? So there will be 2 types of correlations. There is this ambient fluid, hydrodynamic interaction plus this dynamically generated correlation. So that will be very interesting to address.
Even for one particle, it's not been sorted out, probably, right?
Yeah, it's very hard. So it's generally,
Last question.
Thank you, Satya. Actually, in connection with just what you said right now, did you, in the first part of your talk, you talked about all these interactions, such as the different K. So did you look at those systems with resetting?
Not really. So that's Manus. Manus will work on that.
Okay.
It's a hard problem. So it's, no, but you guys looked at the Calogero case at least, some dynamics, right? But not with the resetting. But I mean,
I mean, we have started looking at dynamics of the arbitrary K model, but even that is not sorted.
Yeah,
so
even without resetting, to calculate, for example, just under model A dynamics, for example, it's very hard. I mean, so
Okay, yeah, I think we have to move to the next talk. So thanks, Shotto, for a great talk. Okay, so the next talk is by Hugo Tuchet, and he'll talk about large deviations of linear diffusions.
Tell me earlier. I'm going to keep it. Yeah. Good morning, everyone. I'll start by thanking Sanjeev for the organization of the conference, for the invitation. Congratulations on 75 years and all the best for the next 75 years. I'll be presenting some work done with two students, a PhD, Johan Dubuisson, who's now working in Vancouver, and then Tamun Emulva, who was a master's student. So this is recent work that we just published this year on large deviations of linear diffusions. So this is the context. So what we're interested in is to study fluctuations of what we call observables. I'll come to define this in more details, but this is overall the context. So we look at some non-equilibrium systems. We can measure some quantities about that non-equilibrium system, and then we want to find the statistics of that observable quantity. So for the modeling, we use a Markov process to model the system itself. And then the observable is calculated over a long trajectory of the system. So that capital T there is the integration time. So we just observe the system from time 0 to time capital T. We measure this quantity, and then we want to find the distribution of that quantity. This is very difficult in general. You can do this only for special cases like Brownian motion, but as soon as you consider a general Markov process, this is very difficult to do, but we know that in many cases the distribution will have an exponential form with the integration time, which we call the large deviation approximation. And then the wiggle there just is there to mean that the dominant part of that distribution, in fact, is that decaying exponential, and then studying that form is part of what we call large deviation theory. And the way to do this, and then I'll be using this in the talk, is that we don't study the distribution directly, but we study the generating function. And then when you have an exponential form for the distribution, you also have an exponential form for the generating function. So whatever information you can extract from the generating function, so in this case, the dominant exponential form of the generating function, then you can go back to the distribution and then, for instance, get this exponent, which we call the rate function, from this exponent, which we call the scale commune generating function. And again, I'll come back to this in the detail. So this is kind of the picture. We can measure or we can simulate trajectories of the system, many of them, and then we can reconstruct the distribution by simulating or observing many trajectories. And then if you have a large deviation approximation, what this means is that you have, if you observe for longer and longer time, you see the distribution actually collapsing into some points. That's the typical value of the observable. And then we're interested in the exponentially rare fluctuations around that typical value. And this is described by this function, this I of A, which we call the rate function. So at this point, if you have the distribution, then you can understand actually what's the behavior of the fluctuations or the likelihood of the fluctuations. But we want to go one step further, which is to understand actually how fluctuations are created. And this is something that we've studied more recently in terms of what we call the effective process. So the idea here is that if you look at a fluctuation, so in the tail, if you look at a rare event, you want to look at all the trajectories that actually led to that rare event, so you can color them differently. And so this is a family of trajectories. This is just kind of a subset of trajectories that is responsible for the fluctuation that you see. And we want to describe that family as a different Markov process. And then you can show that in a long time limit, you can indeed describe just this subset of trajectory as a different Markov process, and then you can write explicitly what that Markov process is. So this is something also that I want to do. So people have been doing this for quite some time for many different systems, I would say very active in the last 10 years, although large deviations, the theory itself has been around for more than 20 years, but in physics, actually, it's been adopted and used quite a lot in the last 10, 15 years. So it's been applied for for many different systems and many different observables. So here I'm just listing a few things like Markov chains, random walk, jump processes, and then in this case you can look at occupation observables or current type observables. It's also been studied in the context of diffusions, so kind of Langevin equations, stochastic differential equations, modeling different systems like laser tweezers, for instance, experiment that Satya just mentioned with laser tweezers. And in this case, you can measure different observables like the heat exchange between the particles and the heat bath, or the work done by the laser tweezers on the particle. And then people have started looking also at active versions of diffusions and looking at things like the entropy production, which is another observable. And there's been lots of work also in the last few years on many particle dynamics. So I'm putting an example here. This is the exclusion process. So you have many particles moving on the lattice, and then they can move at different rates. And then for the exclusion process, the rule is that you cannot move if the site is occupied. Otherwise, you can move at a certain rate. And then you have incoming rates at the boundaries, which can be different. And this will model a particle reservoir. And then you can create a kind of steady state current into the system. And this will be the typical current that you see, but you can also study fluctuations of the current for that system. So this is also a Markov process underlying the system, modeling the system, and then you can measure observables like the density at a given site or the current created over the whole system. And this has been studied a lot by Bernard Derrida and then many other people in France in particular. On top of this, so if you look at this, actually, there's some cases that you can solve exactly. So you can find the large deviation rate function exactly, but there are not so many examples. So I've always been on the lookout for explicit examples, and there's quite a lot on the level of diffusions when you look at the linear case. And so people in maths have, for instance, looked at quadratic observables, which I'll define later on, and entropy production. Also, Anupam and Sanjeev actually, and also Arnab have looked at coupled oscillators. So if you look at particles that are coupled with quadratic potentials and looking at various observables like the work created or the entropy production of the setting. And in this case, you can obtain exact solutions for the rate function, the scale generating function, and then various other things. And so this is the seed of the work. So what we've tried to do is to kind of build a general theory for these linear systems and looking also at the general class of observables and trying to find an explicit solution for this. And this is what I want to present. So it kind of englobes or generalizes all of these studies which were done for specific systems and specific observables, and I'll come back to those actually. Okay, so the model that we'll take as the underlying model is the linear diffusions in Rn. So this is n-dimensional space. So you have the state, which is that bold state there, x of t, which is, now it's a linear diffusion. So the drift is actually a linear function of the state. So it's a matrix multiplying the state. And then this is perturbed by a Gaussian white noise, so by increments of Brownian motion. And the Brownian motion lives in m-dimensional space. So the noise actually doesn't have to be the same dimension as the state. This is how you define a linear diffusion in general. M is a n by n matrix. The sigma will be an n by m matrix. And then we choosing m to be positive definite in order to have a steady state. So under those conditions, then you reach a steady state in the Fokker-Planck equation. So this can model many different systems. So I've mentioned laser tweezers, but also if you model linear electrical circuits, and then you take into account the noise, the electrical noise into the circuit, the Nyquist noise, then you can map this also into a linear stochastic differential equation. In control theory, this is used quite a lot too as a model of control systems that are perturbed externally by noise. In this case, not necessarily thermal noise, it can be just external noise. So what's interesting is under the assumption that M is positive definite, as I mentioned, is that you have a stationary state characterized by a stationary density, which is solved the stationary Fokker-Planck equation, which in this case, because of the linear nature of the force, I think many of you know this, you have a Gaussian distribution characterized by a stationary covariance, which satisfies this equation. So this equation is known as the Lyapunov equation. I'll come back to this one. And moreover, you have associated with this in certain cases a stationary current, which is non-zero, which will have this form. So it's linear in the state, and it's weighted by the stationary distribution. And then it's characterized by this H matrix, which is given explicitly like this. So this is quite a nice example of solving a Fokker-Planck equation. Exactly, you just put this, the Gaussian NZs, into the Fokker-Planck equation, and you get all of these results. Now I'll show some examples. So one easy example which relates actually to equilibrium system is the case where you have a gradient drift. Then in the case of a linear example, for instance, in 2 dimension, you can take the drift matrix to be diagonal. It doesn't have to have the same coefficients in the diagonal, but in the simplest case, you can take the same constant. And so this will be a kind of friction coefficient there. If you do the calculation, you find the Gaussian state, so it's isotropic because I'm choosing the same gamma in the 2 direction. And then the current in this case is 0. So the explanation of this is that there's no rotation in the drift itself, so there's no rotation created into the system. If you start with some initial point, it will diffuse back around the origin and then will make a kind of Brownian motion around the origin, confined into a quadratic potential, which is isotropic. So this is an equilibrium system. It's a particle actually diffusing in a potential with a single E bath in this case. So this is an easy version or a simple version of an equilibrium or reversible system. As a variation of this, you can actually put some rotation. And the easiest way to do this in 2 dimension is that you keep the diagonal to be gamma, but you put this rotation, which makes it non-gradient. So in this case, the drift is non-gradient, but can be separated into a gradient part and non-gradient part, which is orthogonal to the gradient force. So this is what's called a transverse diffusion. If you redo the Fokker-Planck calculation, or if you solve the Lyapunov equation that I put before, then you get the same Gaussian density as the original system, as the gradient system, but now there's a current. There's a circulating current, and so you're dealing with a non-equilibrium system. The current actually follows the arrows there is just the vector field for the drift itself, and so the current will follow that vector field, so there will be a circulating current whose magnitude actually depends on the stationary density. So you have less current in the middle because the force there is 0, and then you have a kind of maximum current over some annulus in the 2D plane. And so it's quite easy to understand. If you do simulation, if you start the system here, it will have a tendency to go back to the origin, but following the kind of rotating field, and then it will diffuse around the origin, but whenever the noise actually pushes the particle away from the origin, it will come back with a certain rotation. So effectively, you're creating a current all the time in a stationary way. So you have to imagine that you're doing work into this, and so you're creating a non-equilibrium steady state. So this is one example of a case where the steady state is created by a non-gradient drift force. The noise is still isotropic in this case. I'm still using, actually implicitly, I haven't really mentioned there, but I'm using 2 Brownian motions that have the same amplitude. And then another variation will be a case where you put Brownian motion onto the particle in 2 dimension, but you use different temperatures for the Brownian motion. And so if you use a noise matrix like this with 2 temperatures in the diagonal, then you have, in a sense, 2 heat baths for the particle. So this is a system that's called a Brownian gyrator. In 2D, you have to imagine that this models 2 particles having their own state, so a 1-dimensional state. You can put a coupling between the 2, and then they will each have a kind of friction linear force, and then a linear coupling between the 2, and then 2 temperatures for each of them. So in this case, this is the drift matrix. You have the kappa, the coupling, the gamma is the friction, and the kappa, the coupling, actually will induce this non-diagonal term there. You can do the calculation. It's very similar to the transverse case. And then here you also have a non-equilibrium states. So you have a current actually being circulated around the origin. But now the fact that you have 2 different temperatures will tilt the system slightly. And here you have a non-equilibrium state. For this, you need 2 different temperatures and a coupling. If you put the coupling to 0, then there's no current, and then if you have 2 equal temperatures, then you have no current also. So you need, as a necessary and sufficient conditions, the coupling and the unequal temperature. So these are kind of examples that have been known for quite some time, and they're nice actually if you teach statistical mechanics non-equilibrium statistical mechanics because they're kind of easy to understand Gaussian examples of cases where you have equilibrium behavior and non-equilibrium behavior. Okay, so this is what I want to study now in any dimension, and I want to not look at the system itself, but observables. So what kind of observables will we be looking at? So here we're defining 3 general forms that we can study and then find exact solutions for. So the first one is what we call a linear form. So you have the state, and then you just have an integral of the state in some way, but you can weight the different states differently. So the way that you will weight the states differently will be with this vector eta. You can also find an exact solution if you consider quadratic forms, quadratic observables. So in this case, you have the state. It's a quadratic form of the state integrated in time, and then the quadratic form will be defined by this Q matrix. And the final one that we'll consider is relevant for physics is what we call current type form. So in this case, you have a linear integral of the state, but just not integrated in time. It's integrated as a stochastic integral with the increments of the process itself. This you can picture essentially as being the integral of the state times the velocity. Okay, so if you divide dx by dt, then you have an integral in time, but you actually put there the velocity. If you look at physical models of non-equilibrium systems, each of those actually will arise in different ways and will define different observables. So for instance, if you look at the work exchange in a laser tweezer experiment, and then you model the diffusing particle being controlled by the laser tweezer as a stochastic differential equation, then the work is actually of this type. It will be the force times the displacement. So mechanical work has a current type form. The same with the heat exchange, the same with the entropy production. They're of this form. If you look at residence time, actually, it will be more of the linear form. And in control theory, people look a lot at these quadratic forms in terms of quadratic loss functions in control theory. So all of these actually can be realized if you want physically or in terms of control systems. And if you do simulation or experiments and then you track these observables, what you see again is always the same thing. You see that as you perform a longer and a longer experiment, the observable converges to some typical values. You'll see overwhelmingly the same value, that's the typical value, but you still have some fluctuations around this typical value that are exponentially rare, and this is described by large deviation theory, and this is what I want to describe. So the distribution of the observable for all of those will always have this exponentially decaying form with the integration time, and what we want to calculate is the exponent, this I of A, that will tell you exactly how the decay goes with time, and this is what we call the rate function. Okay, so how do we do this in practice? So we follow this theory of large deviations that has a long history actually, but most of it was developed in the 60s and 70s by Stanisław Varadin and then Donsker some time ago, and then generalized later on by Gartner, and then there's a long list of mathematicians who've worked on this. And essentially, we calculate this rate function via, as I mentioned before, not the probability directly, but the generating function. And the generating function has this exponent that I mentioned before, this lambda k, so that's the exponential form of the generating function. In the exponent, you're going to have this function lambda k. Now, it just so happens that for a Markov process and then some additive observables of Markov processes, the lambda k actually can be obtained from a spectral calculation. It corresponds to the dominant eigenvalue of some linear operator, which is a deformation or a perturbation of the Fokker-Planck generator. So I'm not putting the details. I'll show you some explicit examples later on. But the upshot of this is that you basically have to do a spectral calculation. You extract the dominant eigenvalue. That's your lambda k. And then you can put it as a Legendre transform. You calculate the Legendre transform of that lambda k, and then you get the rate function. So with this, you get the distribution up to exponential order. So that's the rate function. This is not an easy calculation in general because it's a spectral calculation. Essentially, it's as difficult as doing quantum mechanics. The spectral problem is also useful for defining what I've mentioned before, which is how to understand how fluctuations is created. And this is the fluctuation process. So what I've mentioned before is that the subset of trajectories that gives rise to a certain fluctuation can be described by a Markov process. So in this case, it will be described by a modified stochastic differential equation. And then we know from the theory that this modified stochastic differential equation has a modified drift, and it's the original drift plus the diffusion matrix, and then the gradient of the log of R of k, and R of k is the eigenfunction that's related to the dominant eigenvalue. So from the dominant eigenvalue, you get the rate function, and from the corresponding eigenfunction, you get the modified drifts that gives you an explanation as to how fluctuations are created. So again, essentially, you're looking at a fluctuation. A, from the rate function, you'll get that k there. K will parameterize that fluctuation process. It will change the drift. It will push the drift in a different direction. And if you simulate this fluctuation process, basically, you'll see exactly those trajectories that you would see in an experiment as creating originally in the original system those fluctuations. This is a new, yes? D is sigma times sigma transpose. That's the diffusion matrix, okay? And sigma is the matrix multiplying the noise. Now, this is a new stochastic differential equation, so it has a modified stationary density. It has a modified current. So I'll denote this by the P star K and then the G star K there. And K, again, is that parameter of the fluctuation process. You have to see it, in a sense, as a temperature. It's kind of a parameter dual to the fluctuation you want to see, so it's a bit like an inverse temperature. So I can parameterize the fluctuations either in terms of their value or in terms of the K parameter that will be associated with a given fluctuations via this relation.
Sorry, I'm missing. What is RK again? Sorry.
RK is the eigenfunction corresponding to the dominant eigenvalue of this modified operator. So in order to get the rate function, I need to solve a spectral problem involving this linear operator Lk. The dominant eigenvalue will be my lambda k. The dominant eigenfunction is Rk. And so this will define the modified drift. So with that spectral calculation, I really solve the whole large deviation process. I get the likelihood of the fluctuations, and I get an explicit physical process that tells me how those fluctuations are created in time via a different Markov process. Now, this part was known for quite some time, actually, basically from Varadin and then more specifically from Gartner. But this part is much more recent. This is work that we've done in the last 10 years. Okay, so I want to apply this theory now going back to the linear diffusion case, the general case of linear diffusions for the three types of observables that I've defined. So the way we do this is actually we do not solve the spectral problem. What we do is that we can solve the generating function exactly because we have a linear process, and then the observables are basically linear or quadratic, and then in this case we can solve for the generating function. So this is the generating function, so it's the expectation, it's the exponential expectation. So you have k, t, this is the observable, which is integrated up to the time now small t, and then you actually condition on starting at a specific point at time 0, so this is the generating function for that specific initial condition, and then up to time t. The generating function has an equation very similar to the Fokker-Planck equation for its evolution. It's called the Feynman-Katz equation. You can derive this using path integrals, or in maths they use different techniques, actually stochastic calculus to derive this equation. And then for a linear process, and then for the linear and quadratic observables, it has an explicit solution, which is this form here. So it has a kind of Gaussian form here, and then a trace form in the exponential, and then under some conditions, it will have a long time limit, a stationary limit, where now the matrix B won't depend on time. The matrix B itself will reach a stationary limit, and so the generating function will have this exponential scaling in time, and so from this you can extract the large deviation results. So B is a matrix, right? So this will be a quadratic form, so that defines a kind of Gaussian function here. And here you have D times a matrix, and then you need to take the trace. This will give you a number, and that number in the long time limit will be exactly the scale cumulant generating function that we're trying to find. BK actually satisfies a Riccati type equation. I'll show that equation on the next slide. And then under some conditions, you can show that the time-dependent Riccati equation will go to a stationary solution. In fact, it can have many different solutions, and so you need to select the right one, which will be this BK star matrix. So that we call the Riccati matrix. And then the eigenfunction, the RK that we need to define the fluctuation process, is always actually, when you look at the scaling of the generating function, it's always the bit that comes in front of the exponential scaling. Okay, so that comes from the theory. So from the RK, I can plug this back into the theory, and so I can find that the effective drift for the solution for the linear process will always be also a linear diffusion. And this is kind of unexpected and a nice result, the fact that all these fluctuations for the 3 types of observables that I've mentioned before will always be created by another linear process. So it doesn't change the fact that the drift is linear, and I'll come back on this. So this is kind of the summary of the general results. There's lots of calculations to get there, and then the main object is actually this BK matrix that we need to find, which will depend on D, on M, on sigma, and then it satisfies a Riccati matrix equation, which is kind of big in itself. So I'll show you the calculation for one particular case, one particular case of observable, which is the current type observable, which is more relevant for physics. So this is the definition again of the general observable. You have the state being integrated in time multiplied by the increment. So the general observable will be defined by this gamma matrix here, and then the form of gamma will depend on the physical observable that you consider. So if it's the work, then the gamma will be essentially the M. If it's the entropy production, it will be something else. But all the results will depend on that gamma matrix that you have. This is the explicit expression of the tilted generator. So the eigenvalue, which will be like the dominant eigenvalue I need to find, will be the dominant eigenvalue of this differential operator. Okay, so it looks a bit like a Fokker-Planck operator. You have here the Laplacian part, but it's modified because now you consider the observable, so you do a large deviation calculation. You're not doing a Fokker-Planck type equation. This is the form of the Riccati equation for the BK matrix, so it's quite big. And then it's a Riccati matrix because you have a BK term. So a Riccati matrix is always of this form. You have a constant term, you have these kind of conjugate term, and then a Riccati matrix equation is second order in the matrix that you want to find. So we have a form of what we call algebraic Riccati equation, and so the matrix BK that we need to find is from this equation. For this current type observable, also the modified drift matrix will have this form. So against BK, and then will depend on the gamma there. And so at the end, you find, because you haven't changed the linear form of the drift, you find still that the stationary state is a Gaussian density with a modified now covariance matrix that satisfies a modified Lyapunov equation, but it still has the same form of a Lyapunov equation. And then the current will also be of the form that I shown before for linear diffusion, because again, the diffusion hasn't changed. It's still linear, and so now you need to find this modified H matrix, and it has the same form as the form that you would find for linear diffusion. So this is the general solution that you'll find in the paper for current type observables, and what we do is that we give the solution also for the linear type observable and then for the quadratic type observable. And so you have this will change, but you don't change the fact that you have a BK matrix that you need to find, and then to find that matrix, you need to solve a Riccati equation. All right, so to finish, what I'll do is I'll show one application, which is quite interesting, and so this is a second paper that we worked on with the master student, which is to look at the notion of stochastic area. So this is a notion I've learned actually by reading those papers, and probably like in 2020 or 21, very interesting papers looking at something that we know if you remember your differential calculus from undergraduate, which is that if you have a curve in 2D and then you want to calculate the area enclosed by the curve, you take the line integral, which is x dy minus y dx. You remember this? This is a very nice result. It goes by, it's a particular case of Green's theorem. And then you can generalize this to stochastic processes. So it's quite an interesting observable. And then you have the feeling that it will be related to the current in some way, because you need some rotation actually to create some area. So this is the stochastic area. Imagine that you have a stochastic process moving in the plane, It starts at some point, and then after some time, will just finish at some other point. If you calculate this integral, it's actually the area spanned by the process along the trajectory up to, but the area defined by the trajectory itself with the chord joining the final point to the initial point. Okay, so if you actually close the trajectory, it's the area enclosed by the curve. But if you don't close the trajectory, in most cases you don't close the trajectory for a stochastic process, then it's the area enclosed with the chord joining the initial and final point. Now, I was searching on Google and then found out that actually Levy defined this quantity for the first time. Okay, and that wasn't picked up in the physics paper. So it's quite interesting. There's a string of papers by Levy in the 50s looking at this very quantity for Brownian motion, and he was able actually gradually to find the characteristic function, then realized that you could invert the characteristic function so you can find the exact density of this quantity for Brownian motion, and then you get this second type density. You can calculate the variance, and then the variance goes like t squared. And it's kind of makes sense because we know that the radius of Brownian motion goes like square root of t, so Brownian motion kinds of escape, diffuses, and it makes a kind of area, a stochastic area that will have this density with a variance that grows like t squared. What was noticed in the later papers in 2017 is that you can calculate the expectation of the stochastic area for linear diffusions, and then there's a connection with non-equilibrium system because the area will be non-zero if and only if you have a current. So it's a proxy for non-equilibrium. Instead of measuring the current to characterize the system as being equilibrium or non-equilibrium, you can just measure this scalar quantity, the area, and the fact if it's zero, then you're dealing with an equilibrium system, and if it's non-zero, you're dealing with a non-equilibrium system. So from the point of view of experiments or simulation, it's easier to deal with this quantity because it's not a vector field, it's just a scalar quantity. And it's easy to track. It's a statistics. It's a kind of estimator of something that you can measure.
Substitute 1, 2 is the off-diagonal component?
Yes, so it's, yeah. So for a 2D system, you're going to have the matrix H for the current, and then if you take the off-diagonal part, then this is the expectation of the stochastic area. So in those two papers, actually, you have that calculation for the expectation. So this is the long-time expectation of the stochastic area being given in terms of M, C, and D for the linear system. So what we thought is, okay, we have the expectation. Now let's calculate the full distribution for this. And we can do this because we'll be dealing with a linear diffusion. And this is a current type observable. You see it's linear in the state. It's linear in the state multiplying the increment. So it really has the form of a current type observable. It's just it will have a specific gamma. So we do the calculation. This is the observable again for the stochastic area. The gamma will have this form. It's antisymmetric. What's interesting also with the stochastic area is that, actually I haven't mentioned this, but the way we define the stochastic integral is that we take the Stratonovich convention just for because it's convenient, but the stochastic area is completely invariant with respect to the choice of the stochastic calculus that you use. So if you define the stochastic area as a Nito integral like actually Levy did, you get some number. If you define it as a Stratonovich integral, you get exactly the same number too, which is not the case in general for stochastic integrals. But for this one, it works essentially because it's an antisymmetric stochastic integral. Okay, so this is for this system. So this is the transverse diffusion I've mentioned before. So you have this rotating drift for the force. You have the isotropic noise, and then you can calculate the typical area in this case, the expectation, and then you see that it's proportional to the psi there. The psi is the rotating force at play, making this non-equilibrium. Now, we can use our theory. We can go back to the Riccati equation and try to solve it, and then we can solve it here. It's actually not so difficult because in this case, the Riccati matrix is diagonal. So you only have to solve for a scalar. You can find a scale cumulative generating function, and this is this lambda k there. You can take the Legendre transform, you find this, and so this is the plot of the rate function. So you have a 0, that's the typical value of the stochastic area. If you do a long experiment, this is the value that you'll see. And then you have exponentially suppressed fluctuations according to this rate. So it's much more unlikely to have negative stochastic area. And now I haven't actually mentioned what a negative stochastic area is, but if you remember your differential calculus, you use your right-hand rule. If you have this motion like this, it's a positive area. If it rotates in the other direction, you have a negative area. So if you have counterclockwise, then it's positive. Clockwise is negative. So here I have a counterclockwise dynamics. So the area in expectation will be positive, but I can have negative values of the area because the particle can go against the drift because of the noise, and this will be exponentially unlikely as determined by this branch of the rate function, and so it's more likely that you'll get positive fluctuations of the area. In this case, there's something that we call the fluctuation relation. Is actually a symmetry in the positive and negative branches. They're related by just a linear term, which is related. Actually, entropy production will have something very similar to this, but it's true for any type of current type observables that are related to non-equilibrium. When the psi goes to 0, then the typical area will be 0 because you're not performing any kind of rotation. So when the particle actually fluctuates, in this case, what you see again is that if it departs from 0 because of the noise, it will come back with a certain rotation. So it has to create area. And so this is the non-equilibrium effect. If you don't have that rotation, it can fluctuate away from 0, but it will come back in any way possible. And so it's not creating area in a typical way. Yes, okay. Okay, so this is to describe now the likelihood of fluctuations. So out from this, you can understand actually what type of fluctuations you can get and what the probabilities of those fluctuations are. But we want to go one step further and again understand how those fluctuations are created. So as I said, the main result of the study is to show that the effective process explaining how fluctuations are created actually gives a linear process again. So it will be characterized by another matrix which will have different off-diagonal elements and different diagonal elements. And there's nothing that says that these elements have to be the same, but in this case, actually, you do have the same diagonal elements and the same off-diagonal elements, and so you also have some rotation. So you start with the transverse diffusions, and fluctuations are just created by another transverse diffusions with modified rotation and modified friction. So I'm putting here the friction coefficients in blue and then the rotation coefficients in green. And so these are the explicit results for the rotation and then for the friction. And then we can actually study this for different fluctuations. So here I'm looking at different fluctuations of the area. The blue dot is the typical value of the area. So in this case, we have 1 for the gamma, and then we also have 1 for the rotation. This is what we took actually in the calculation to generate the plot. And then here I'm saying, if the fluctuation is bigger, what happens? So what happens is that the system actually gets less and less friction, so it's less localized, and it increases the rotation. So it's creating more area by turning faster, but mostly by allowing the particle to go further away from the origin. And there's a trade-off between the two because for the very large current, the very large area fluctuation, the current part actually will saturate. So it's not turning faster. It's just the particle can just move further away from the origin, so it's going to make bigger loop, and this is how fluctuations will be created. So it's more likely that a large area fluctuations will be created by seeing a particle going further away than seeing a particle turning very fast. This is what it's telling you. Now for the negative area, what's happening is that you have a current reversal. So the effective psi actually gets negative, so the system effectively is turning the other way around, but the gamma is symmetric with respect to the fluctuation, so it also allows the particle to move further away from the origin. And so this is how a large negative fluctuation will be created. You effectively turn now clockwise, but you move very far away from the origin. Okay, and this is what we see here in these plots. So here we're showing the actual effective current of the effective process and the density as the density plot here. So if you have now a very large current fluctuations, you see that the density is actually reaching out further from the origin, and it's turning slightly bigger, so the arrows are slightly bigger. It's not so easy to see on the plot, but this is what's happening when you look at this. Okay, so you can do this for many different systems. So here I'm just showing one, but it's kind of a template for other applications you can look at. You define for yourself a linear process, so you have the matrix M, the matrix D, and then you look at some specific observable, and then we've done this in the paper for many other systems. So for instance, for the entropy production, for the non-equilibrium work, we've done it for the transverse system, the gradient system, but also for the Brownian gyrator that has different temperature. If you look, for instance, at this system, and then you look at the gradient case, what you're going to have is a 0 here for the psi, so the system is purely gradient. In this case, you also have area fluctuation. So the A star will be 0, so on average, you don't have area being created, but the system can fluctuate, and it can fluctuate as if it turns, and so it can create area as a fluctuation, and then you can do the same calculation here. It's just a particular case, and you'll get the same picture, but it's just translated. So the blue dot, the red dot won't be there, but it will be at 0. So the typical fluctuation of A, the typical value of A will be 0. Okay, so there's more in the papers if you're interested. So it's similar results for other observables and processes, like I mentioned. And the main result, again, is that the fluctuations are created by an effective process which stays in the linear class. And this is how actually we've chosen those observables. If you try to think of other type of observables like the integral of x to the power 3, then it's no longer the case that the effective process is linear. So these observables seem to be like the kind of maximal observables for which you remain in the same class for the fluctuation process. And what you have also is that any kind of fluctuations from these observables are effectively created by modifying the density to another Gaussian and modifying the current also to another linear current. Okay, so one thing I haven't mentioned, which is also in the paper, is that there's a strong control connection, actually. Whenever you see these Riccati equations, if you're familiar with control theory, you will know also that these equations arise in control theory, and there's a way now also to give an interpretation of the effective process in terms of an optimally controlled process that realizes specific fluctuations. And then we're working right now on using those solutions to find linear approximations of systems that are nonlinear, but also observables that are nonlinear, and then using this for the purpose of doing simulation. So in many cases for nonlinear system, the only thing that we have for finding large deviations is to use numerical methods or numerical simulations, and it's difficult to do those simulations without any input. So what we do is that we solve the linear case, a kind of linear approximation, to get a first idea for the input of the simulation, and then run the simulation to make more effective and really solve the nonlinear problem. And so we're working on this right now. So if you're interested in the details, so it's in those two papers. So the general solution is in the second paper, which is part of the PhD thesis of Johan, which he did last year. And then the stochastic area is this paper. And then you also have the references for Levy's work on the Brownian motion, if you're interested. Good. Thank you.
So you looked at the algebraic area, right? So here, I mean, but people have also studied, for example, arithmetic area for Brownian motion is very well known also. This is the work of Wendell and Werner. So arithmetic area, which means that you know, not algebraic area.
Another type of observable.
Right,
yes.
right.
So
you can you make for general linear diffusion arithmetic area? I mean,
I haven't looked actually, so I am aware of the paper. So what Satya is referring to is that this is now the geometric area. It's really the area covered, but you can also look at just the number of turns that you do around the origin. And so this is a different observable. I'm not sure if it's actually it can be put in the form of a current observable. It might be actually. It might be something different.
A lot of work by Alan Comte and Stefan Ouvry and also Wendell and Werner in his PhD. This is actually also, but I don't know whether it can be written as a functional of something, but it will be interesting to see.
It will be interesting, yeah.
I had a couple of questions actually. So you said the fluctuations can be created by this effective linear process, but I take it that these are not finite time fluctuations. I mean, you only talked of large time fluctuations,
yes.
yeah? Because we've looked at these for these finite time processes where also you can solve at least these linear equations.
Yes.
There it isn't that simple. You don't get this effective,
But it's not even clear that you would have a Markov process. In fact, in general, if you look at finite time fluctuations, you cannot describe those trajectories in terms of a Markov process. So if the problem, again, is to look at those trajectories as those trajectories responsible for the fluctuation, if you look only at this subset, which mathematically is a conditioning, you condition the original process on seeing a fluctuation, so this is what I'm writing here. That conditioning is not Markov. At finite time, it's not Markov in general. There's some cases for which this is a Markov process, but it's like special accidents in a way. In general, this is not Markov. So
if you look at like entropy production, or it's not necessarily Markov. Yeah.
So the notion of effective process doesn't even make sense at finite time. So what you can show is that in long time limit, it becomes Markov, like asymptotically Markov.
Right. I mean, so for some of these linear processes, you can solve by these path integral techniques, some of these finite.
So you can solve the generating function in the same way that I've put here. So for linear process, you can solve the Feynman-Katz equation using path integral. And so this is what's done in the other studies, for instance, by Sanjeev, or there was Park also in South Korea did this for specific quantities using path integrals. So what we've done is that we try not to use path integrals, and then you can use Feynman-Katz directly.
And actually, I had one more question. It was if you you can look at general sort of any dimensional process. Have you looked at like what happens if you project, like so if you just say you have an n-dimensional thing, but then you just project it on 2 dimensions, because then it's all these hidden variables and like interesting stuff.
Then it's the same problem. Usually a projection is not Markovian.
I see. Okay.
Yeah. So you could try to do this. I think some people have.
Some people have done that. I think it's kind of, they have some interesting results there.
Yeah. So it's not Markovian in general, and so you could still do large deviations in the projected space, but it will be a non-Markovian type calculation. So in this case, it's not related to spectral theory. You don't have the Feynman-Katz equation, so it's a totally different game.
Okay. Okay. Thank you.
One question. Can you go to slide number 10?
10.
Here, if you you have a drift term in your force function. So in case that drift is not there, would you still be generating those red trajectories?
In the case where?
In the case you don't have the second term, would you still generate those red trajectories with some very minuscule probability?
No, so you see, this term is always there when you look at a fluctuation. So if the I prime of A star, so the derivative of at the typical value, actually the slope is 0. So k equals 0 gives you the typical value. K equals 0 actually doesn't give you any perturbation. So in this case, you have the original system. And this makes sense. The typical value is created by the original system. If you're looking at the fluctuations, automatically the drift will be pushed. It will be changed. And it's going to be changed proportionally to that gradient of the log of the eigenfunction. Okay, there's a lot to unpack here, actually. I mean, I've given presentations for many years just on this result. But this is the end result, is that you have that perturbation coming from the eigenfunction.
Yeah, I haven't quite understood your Riccati matrix B, like what it is, and also how do you solve the equation?
Okay, so it all starts with the Feynman-Katz equation, and then you can show that the solution, actually there's a unique solution to the Feynman-Katz equation, which is this. This is the exact solution. There's an equality here. This is not the asymptotic yet. And then you can verify it just in the same way that if you take the Fokker-Planck equation and then you make a Gaussian ansatz for the density, you can just plug it into the Fokker-Planck equation and you would get the Lyapunov equation. So here you can play the same game. You can put this solution into the Feynman-Katz equation, and then you'll see that this matrix BK in the ansatz, if you consider this as an ansatz, then has to satisfy some time-dependent Riccati equation. These Riccati equations have been studied for a long time in control theory, and they know under which conditions they have stationary solutions. So these are nonlinear matrix equations, so there can be many solutions, an infinite number of solutions, or 0 solutions. And so in control theory, there's lots of theory actually about those Riccati equations. For us, we know that we have large deviations, so we have to have a long time behavior, and so the Riccati equation will have a stationary solution. And so BK as a matrix that is time dependent converges to a static matrix, a stationary matrix. And that defines the ansatz, that defines the solution.
So can you show the equation? I think maybe it's on the next.
So this is for the current type observable, this is the long equation that BK will satisfy. It depends on gamma, the gamma that defines the observable. It depends on M, the M is the drift matrix for the diffusion, depends on D, and then it depends on K, the parameter that will index the fluctuation that you're trying to study. So this is a matrix equation. It's quite daunting actually when you look at this, but in the transverse case, BK is diagonal. So this is why it becomes simple. But for the gyrator, it's not diagonal.
I have a very general question. For large deviation functions, generally in the exponential, the time dependence can be non-linear. And for the distribution and the generative function, the time dependence can be different. Like what class of problems fall into?
Again, sorry?
In the exponential, the time dependence is linear. The cases you studied.
Yes, yeah, they're all linear. So large deviation theory is not necessarily stated for those linears. So here you mean like linear in the time there and the exponential. Yes. So Satya, actually, I don't think you've mentioned large deviations, but there were some plots where you have a left and a right behavior. And in this case, actually, you have left and right different behavior for the exponential. So large deviation theory is not stated only with t. It could be a square root of time or some function of time that increases with time. In our case, actually, and then you can show that for ergodic Markov processes, the large deviation approximation will always involve the time linearly there. But there are other systems that are non-ergodic or funny in some way, like random matrix systems where you're looking at dominant eigenvalues, where the scaling can be very different. It's non-linear in the parameter that you take for the large deviation limit.
Exponential minus square root t, like
yes.
This Derrida and Gershenfeld have studied this.
Like a single phi diffusion, for instance.
The current fluctuation will have it minus square root of t.
So there's still the theory of large deviation is still there. You just have a different scaling for what you need is this concentration and time of the density. Whether it's square root of t or t, then it doesn't really matter.
But can the distribution and the generating function can have different scalings?
Oh, no. If you have one scaling here, it's going to show up in the scaling there too. So essentially, the scaling of the generating function will be inherited by the scaling of the density. So you'll have consistent scaling in the two.
Thank you.
Yeah, I have a question. Like this, using the method like which we did it in the paper, so you can in principle like find out lambda k formally. Can you now show that lambda k basically consistent with this Riccati equation?
Oh, yes. So we went back to all the examples that you guys have studied, and then the example of Park and No, and then it's the same result. It has to be.
But it's not like, for example, that linear chain, right? It's quite complicated, like this harmonic chain which we did on. So there we had some formal expression for this thing, but it's not evident that like
no, this I haven't checked. So yes, this
right, because it's like a very
because you have a very complicated drift matrix because you're looking at n particles interacting in a harmonic way. So yes, this we haven't done. So what we've done is to go back on the simple low-dimensional examples for which there was the solution obtained by path integrals, and then our solution is the same.
The other one would be
There's also an open problem is that in maths they looked a lot at the quadratic observable, and they have another formula for the quadratic observable, and then it's not clear that it's the same that we find. I mean, so for some example we see that it's the same, but they have a kind of a spectral formula which doesn't look the same, but
Okay, maybe I'll ask one last question.
Okay.
For this effective process, I mean, like in practical terms, is it useful because you have to find like first the eigenfunction of the tilted generator, right? So then in practical, like if you really want to look at large deviations in an, is it useful, finally, this effective process?
Well, it's included in the calculation. If you're trying to find the dominant eigenvalue, in many cases you'll find the corresponding eigenfunction. So what we're doing here is that we're bypassing completely the spectral problem, right? Because we find the scale common generating function in a non-spectral way exactly, and then we find the eigenfunction also exactly without doing it's just by solving the Feynman-Katz equation.
But not for the effective, you need this in the effective equation, right,
Yes.
finally?
Yeah. But the RK is always this form, so it's also given by this Riccati
But
matrix.
then what do you use the effective equation for? Like, and you can't use it to get better estimates of the large deviations, right, in, let's say, numerics.
Oh, no. So this actually solves the large deviation. As soon as you have the effective process, you're done. I mean, you have the large deviation function, and then you understand how fluctuations are created. So you don't have to do simulations at this point. If you wanted to do simulation to see really how the process generates fluctuations, you could do this, but all the physics is included in the description of that effective process.
Okay.
What I'm saying in the conclusion is that we use this as an approximation for solving nonlinear systems using simulations. So we use the linear solution as an input to the importance sampling simulations for finding rate functions for nonlinear systems.
Okay. Okay, so let's thank all the speakers.
Thank you.
And I guess we start at 11. It's already.
Yeah, so maybe we start at 11:45.